Okay.
Wonderful. Thank you, Allison. Can you hear me okay?
Yes, perfect. Thank you.
Well, great to be here, and thank you for the invitation. Great to see all of you. What I thought I would do today is you likely, if you've attended similar talks in the past, have heard about Alzheimer's disease, have heard about the pathologies of Alzheimer's, the progress that we've made as a scientific community in that domain. But I thought I would focus on something a little bit different, kind of the counterpart to that, which is not so much about Alzheimer's and the pathology of Alzheimer's, but more how do we keep our aging brain feeling and operating like a young brain? So that's the story that I want to share with you today, and we'll do this kind of in a normally this is a format that I really enjoy doing with a live audience because we can kind of go back and forth. But I'm just going to use the divisive rhetorical questions instead, and we're going to do this like an episode of MythBusters, okay? So the way this is going to work is I will start with the myth, and we'll talk about why this myth is not true. And there's several of them that I want to share with you today. The first one I'm sure you've heard about before, which is that brain cells slowly degenerate as we get older. In other words, there's sort of a progressive cell death as we get older. Now, the interesting thing about this common wisdom, which has been around for quite some time, is that if you actually look at the brain, its structure, at least in a healthy aging brain, you don't see evidence of this neurodegeneration. Now, aging brains don't just deteriorate. That's not really what happens with age. It certainly happens in Alzheimer's disease. We can talk more about that. But in the context of aging, there are changes that happen, but they're not neurodegenerative. So, what kinds of changes actually happen? We know that even though there's no loss of cells, there's a loss of the ability of the cells that are still there to make new connections. And that's one of the really important things that brain cells do. They connect with each other, they form what's called synapses. And constantly, every day, as you're doing this right now, as you're sitting around reading the paper, watching TV, talking with friends, your brain is making new connections. And it turns out as we get older, our ability to make those connections slows down just a little bit. It's not as efficient, it's not as fast as it once used to be. Now, one of the things that we know happens with age is that you have a lot of competing things for your attention, a lot of things that are changing about your body, about the environment, and the brain constantly has to allocate resources to the kinds of challenges that you're meeting on a day-to-day basis. Now, what that means is that as changes and demands or as the environment changes, and that requires that you shift the brain to be able to accommodate those shifting demands. So brains, as we get older, compensate and adapt as opposed to deteriorate and degenerate. And that's a really, really important piece that I want to make sure that everybody takes home from today is our remarkable ability to adapt and compensate for the changes that are happening around us. Me give you a couple of examples. So this is a comparison. If I move my mouse on the screen, can you all see it, by the way? Terrific.
Yes.
If you compare a young monkey to an older monkey, and monkeys are just easier to be able to look at their brains and stain their neurons. So this is just a single brain cell. And you look at the brain cell itself, you don't see much of a difference in terms of the qualitatively sort of the difference between those two brain cells. But if you zoom in very, very closely on just this little branch here, you can see a slightly different picture. Here's what's called a dendrite, one branch off of this cell. And here's that same kind of branch in the older monkey. Now, what you can tell very quickly is that the number of small protrusions that come off of this dendrite is smaller in the older monkey than it is in the young monkey. And it turns out that each one of these little protuberances, each one of these little protrusions, is where you make a connection. These are called dendritic spines, spines on that longer dendrite. And that number goes down as we get older, and the degree to which it goes down predicts how well that animal is able to learn and remember. And the same is true of rodents, the same is true of humans. I'm just showing you the monkey because it makes a nice connection. So we don't lose the cells, we lose the connections. Okay, fewer spines, that's the possibility of connections, which goes down. Now, this is a complex slide, and I don't need you to remember everything about this slide. I just want to go over a couple of things that I think are really important in this slide. And the idea here is that as we get older, we exhibit a lot of compensation. But I want to kind of make that very concrete for you. What do we mean by compensation? If we start here on the left, the idea is that if you start with experiences that you go through during your life, there are certain experiences that will enrich your neural resources, things like education, multilingualism, fitness and leisure activities, social and intellectual engagement. All of those things lead to an enrichment. Okay. On the flip side of that, you look at the bottom here, what's called neural resource depletion. These are the negative things. You might imagine that things like depression, head trauma, stress, vascular disease, low socioeconomic status, having risk factors for Alzheimer's disease, all of those things lead to a depletion of neural resources. Now, this happens in the context of the aging brain. You have things that are positive and things that are negative, and both of those are acting on brain structure and function. And people like me that study the brain do a lot of measurement at this level. We study brain structure and function in extreme levels of detail. We can look at different levels of pathology in the brain. We can look at volume of different regions. We can look at how effective the connections are in different regions. We can look at how is it that the brain is able to carry out daily function. So that's where we do a lot of our measurements. But then the other really interesting piece here is this compensatory scaffolding idea. Now we know that there's positive influences and negative influences as we get older. But what happens as we are trying to maintain our level of cognitive function? You see this scaffolding piece. And scaffolding is being able to maintain a lot more of the positive and mitigate a lot of the negative as we get older. So learning new things, exercising, meditating, stimulating your brain, all of those things lead to positive compensatory scaffolding, which leads to higher levels of cognitive function, and the rate of cognitive change is not as steep. So even when we talk about there's age-related decline, that decline can actually be quite subtle, much like decline in any other system that you have in your body. And when you think about this, the brain is not all that unique compared to other systems in your body. As we get older, we start to experience aches, we start to experience pains, we start to experience different issues with our organs, whether it's kidneys and liver, all of those kinds of things start to need a little bit more of our attention. We joke sometimes that we can't operate the same way that we used to when we're young. Well, the brain is the same way. It just needs a way to be able to adapt to those changes. It needs our assistance, and that assistance comes in the form of enrichment. We'll talk a lot more about that today. This is one idea, again, that makes it very concrete, the notion of reserve. And I'm sure you've heard about this idea before. The notion here is very simple. Those who have had a lot of enrichment, especially earlier in life, can have much more reserve, which allows them to handle an increasing level of pathology, say from Alzheimer's disease, and not have clinical symptoms. So if you look at how test scores, for example, on a memory test change as a function of Alzheimer's disease neuropathology. So this is increasing pathology, and this is higher test scores, lower test scores. You can see that somebody with low reserve might start off at a lower level, and then they decline over a longer period of time. Someone with high reserve might start off at a higher level. They might always be performing better, and then they maintain that level for much longer. You see the difference in time between these two. So that means their brain can handle higher and higher levels of Alzheimer's pathology without feeling the change so much. But it gets to a point where then you see this decline. We see the same thing in terms of diagnosis and clinical severity. Those who have high reserve might change much later in the game, but it might be a little bit steeper. And those who have low reserve might change earlier, but it's less steep. Okay, so what about this reserve? What everybody wants to have reserve, right? How can we have more of this reserve? And I'll simplify it for you. There are many things that go into this formula, but essentially it is based on your lifelong experiences. It's based on your baseline cognition, so what you start out with. It's based on flexibility. That means the brain has to have the flexibility to shift in and out of different states. Social interactions. So when you have higher levels of social interaction, this one is particularly important, especially for retirement. See, retirement is one of those really crucial forks in the road. And there are many that retire but have clear plans for what they want to do post-retirement. And I don't mean having another job or starting a business necessarily. I just mean remaining engaged, remaining socially connected with people. For some others, that does not happen. Prior to retirement, they had a lot of social engagement in their job, whatever it may be. And then once they retire, they become isolated. And that becomes very, very challenging. So maintaining that level of social interactions well into older age is important. Physical activity, you'll hear me talk about physical activity a lot today. We know that's one of the best ways to be able to maintain higher levels of cognitive reserve. So those are the things that we know seem to have this positive impact on the brain, seem to scaffold the brain to compensate and adapt given levels of pathology. And what that means is that two people can have the same exact level of pathology in the brain. One of them is declining, one of them is not. And the answer is what gives? And the answer typically is some combination of these variables. Okay? So going back to our myth, brain cells slowly degenerate as we get older, I think we can say this one is sufficiently busted. Provided that we have scaffolding, provided that we have the tools that we talked about, this degeneration does not happen. Let's go on to another one that I'm sure you've heard about before. Once we reach adulthood, our brains stop making new cells, right? You're born with all of the brain cells that you're ever going to have. And as you get older, you don't make any new ones. All they do is just degenerate. Turns out this one is also challenging, even though it's been common wisdom for many, many decades. Turns out that for the most part, we don't make new brain cells as we get older. For the most part, with a couple of exceptions. There's two places in the brain where we continue to make new cells. The process is called adult neurogenesis. Neuro, brain cell, genesis, birth. So birth of new brain cells. Now, those two places are really interesting. One is what's called the subventricular zone. The subventricular zone is here near the ventricles. The subventricular zone is really important for feeding into the olfactory system, our smell system. But the second one is even more interesting, what's called the subgranular zone, which is part of the hippocampus. The one area in the brain that you might have heard about before. It is famous because everyone knows that the hippocampus is important for memory. And most people that think about what happens to the aging brain, what happens to an Alzheimer's brain, the hippocampus is the very first place to start to change. Well, it turns out the hippocampus is also one of the two places in the brain that continues to make new cells as we get older. And we think that has something to do with continuing to be able to learn and remember well into older adulthood. Here's one study I want to share with you that I think is just fascinating. This was the proof that we continue to make new brain cells. And I share it because it's such a weird study. So the way that this study worked is that they went back and looked at nuclear bomb-derived carbon-14 concentrations. They essentially looked at a carbon dating mechanism. And by doing this, you can go back. So at the time, this is in the 1930s, 1940s, there were lots and lots of atomic bomb tests that were happening that left the atmosphere essentially covered in carbon-14. Carbon-14 has a very long half-life, stays in the body, stays in the brain. You can actually use this to carbon date cells. In other words, you can tell when those cells were birthed. And when they did this study, they determined that actually there was continuous neurogenesis, continuous birth of these cells, evidenced by carbon dating well into older adulthood. So those who were born in the 1950s, 1960s were able to date those cells and say those continued to thrive. And I share it again. There's many, many other types of evidence, but this one is just so interesting and so quizzical because they use carbon dating to be able to figure out the fate of these cells, something that a lot of neuroscientists would not do. But in this case, they collaborated with some really interesting physicists and engineers and environmental scientists That's the kind of thing that can lead to these interesting insights. Now, the reality, of course, is that yes, aging brains continue to make new cells in the hippocampus, certainly not at the same level that we did when we were 10 years old or even 20 years old. But from the age of 20 onwards, you can see the adult level is pretty low but stable, does not go away. We can still generate new cells in our brains, presumably until, well past the eighth decade. So all of that is to say, this myth that once we reach adulthood, we stop making new cells is also busted. Pretty good evidence that we continue to make new adult cells. This should all be very good news, by the way. I hope that I'm conveying good news here. Let's go on to our third one. This is a fun one. And maybe those of you who are on camera can just give me a little show of hands. How many of you have heard of this before? You only use 10% of your brain. Yeah, I heard this one coming up in neuroscience. You only use 10% of your brain. Then I became a neuroscientist and realized that it could not be farther from the truth. But it's rampant. It's all over Hollywood. If you've seen films, terrible films like Lucy, or films like Limitless, they all talk about, man, what would happen if you could just unlock that other 90% of your brain? You would have near superhuman abilities. Now, the premise here is not entirely, you know, fictional, because if you put the person in an MRI scanner, for example, look at activity, what you'll see is that, different parts of the brain are active at different times. And it might give you the illusion that we only can access a small amount of our brain. But it turns out the reality is we access our entire brain all the time. In fact, it's incredible how much activity is happening in the brain constantly. Electricity, chemistry. It's a constant flow of information, even while you sleep, even while you're sitting there pretending to do nothing. This symphony continues. And it's such a beautiful thing because when you think about it, if we did not use 100% of our brains, actually our brains would degenerate and deteriorate. So we know this to be true. We know that small lesions, even tiny little pieces of damage to the brain because of a stroke or a traumatic brain injury can cause some serious deficits. Now, if we only use 10% of our brain, we'd have to get seriously unlucky to hit that 10% if there's damage. But that's not true. We can get damage to all sorts of different parts of the brain, and each one seems to be associated with a focal deficit. Every part of the brain is important. Every part of the brain is functional. We know that our brain is only about 2% of our body weight, but it burns 20% of our energy at rest. That's if you're not really engaging with anything. Just sitting there at rest or while you're sleeping, you're burning 20% of your energy just in your brain. It is incredibly metabolically demanding or metabolically hungry. Now, when we do neuroimaging studies like the ones that we do in my laboratory, we also find out very, very quickly that the brain is constantly active. Even when we do what's called a resting state, functional imaging or functional MRI, resting state doesn't mean much. Our brains don't really know how to rest. They're constantly working, constantly going through glucose and oxygen, the two things that are super important for our brains. We also know, and this has been wisdom in neuroscience for quite some time now, the idea of use it or lose it. That means if we had a lot of unused brain matter, it would deteriorate. It would be eliminated and go away. The reason why our brain is constantly active is because it needs to keep those connections going. It needs to keep refreshing them, keep learning new things. A brain that is not learning, a brain that is not changing, is essentially dying. So given all of those things, we know that we are using near 100% of our brains all the time. Couple of different pieces of evidence. This is FDG PET. So FDG stands for fluorodeoxyglucose. It is a radiochemical tracer that is used in PET scans. So PET scans are positron emission tomography scans. Those are scans that you can get injected with a small amount of radio tracer, and then you lay down in a PET camera and get an image of your brain's metabolism. Some of you might have done PET for things like breast cancer, for things like imaging amyloid in the brain, or things like that. Those PET scans can be very helpful to being able to look at levels of pathology. In this case, it's levels of metabolism. And when we do those scans, we see that, again, the brain is highly metabolically active, constantly consuming glucose. And by the way, it has a knack for extracting glucose from pretty much anything you eat. So that does not mean you should just be eating simple sugars all the time. It's very, very good at breaking down pretty much anything you eat and getting glucose out of it. Here's the other one. We do a lot of this in my laboratory, functional MRI, what's called a default mode network. Default mode meaning it's the mode that is constantly active when you're doing pretty much nothing. And you can see lots and lots of activity throughout the brain. Interestingly, the back of the brain, this is what you see here. This is the front where the nose is. This is the back of the brain. Lots and lots of activity in the back of the brain. That's where our visual cortex is. And when the person is lying in the scanner, we're not showing them a movie. We're not showing them anything. And yet their visual cortex is going off. And that happens when you start to imagine things. When things start to cross through your mind that give you a nice visual, it engages your visual cortex. Same thing with things that you might hear, people's faces that might be a fleeting thought. Anytime you have those fleeting thoughts, your brain is active. So going back to our myth, you only use 10% of our brain. I think this one is also sufficiently busted. But there's this second part to it. Neuroplasticity can help you unlock the rest. Let's talk about that for a minute. What do you mean by neuroplasticity? The word plasticity itself is an interesting one. When something is plastic, it means it has the capacity for change. That means it can change easily, right? And neuroplasticity is really about increasing that capacity for change as we get older. And there's only one way I know of to do that, and that is constantly learning. And if there's one really important take-home message that you take from this, is that continuing to learn and engage with learning new things as we get older is the absolute best way to protect the brain against things like Alzheimer's disease. It's not foolproof, it's not 100%, but it is the one thing that we know we can control. Okay? Couple that with healthy stuff like exercise and good diet, that's the recipe for success. Some of you have heard this before. Can't teach an old dog new tricks. It starts to become discouraging as we hear that as we get older. Can't teach an old dog new tricks. Well, we're not dogs, but it turns out we can learn new tricks. This is a fun one. This is juggling. Now, I am no expert juggler, and there's no reason for any of you to become expert jugglers, but in this particular study, they took people that have never juggled before and tried to make expert jugglers out of them. And it turns out that when you do this, when you learn a new skill, whether it's juggling or my favorite one these days, pickleball, right? Learning any of these new skills actually changes your brain, changes brain structure. So this is a part of the brain that changes in response to this juggling training. Here's the change in gray matter. This says green matter, I should say gray matter, I apologize. And what you're seeing here is the change from the first scan, which was pre-training, before they learned, to after training. And you can see that large increase. The interesting thing about this is that then they spent 6 weeks after that not training at all, and then scanned again. And that's the third scan that you see here. It didn't go back all the way down to baseline. It certainly went down, but there was still savings, is what we like to call it. So learning new things changed the brain. And even after a period of not learning after that, the brain change was sustained. It stuck around. And that's the kind of plasticity that we want to see. Now, you can do this in young adults. You can do it in older adults. It works beautifully. This is one other study that was done in older adults. This is by some of our colleagues on the East Coast at University of Pittsburgh. And what they did here was just look at the impact of physical activity, exercise. And we're not talking about extreme exercise. We're talking about moderate type of exercise. So think brisk walking, jogging, nothing too strenuous. And you can see over a 6-month period, a 1-year period, the volume of the hippocampus, which I told you before, really important for learning and memory, increased as a function of exercising, where it was decreasing as a function of something like stretching with no real aerobic load. That was a good control because normally you do this in group classes, and we wanted to make sure, or they wanted to make sure that they controlled for social aspects, for all other things that might change. Let's say you're just going to the gym and meeting with people. Well, is that enough? Not really. Turns out you need to actually have a, a, a real exercise component to make this change happen. And the great thing about this is that the level of this change in exercise was associated with the increase or change in what's called BDNF, brain-derived neurotrophic factor, a brain chemical that actually is really important for brain cell health. Brain cells release BDNF to keep themselves healthy and happy and allow them to recover from injury and all sorts of wonderful things. So we talk about BDNF as like the happy juice of the brain. And no, I don't have it in pill form. Otherwise, I would give it to everyone, unfortunately. But that change was also associated with change in memory performance. So not only did the hippocampus get better, BDNF levels went up and also memory got better. So can physical activity, can training, can this kind of plasticity change the brain in a positive way? You betcha. And for older adults, these are all adults over the age 65. So then going back to our myth, you can't teach an old dog new tricks. Yeah, we definitely can bust that one and say we most certainly can. And there's lots of evidence for how we can. And one of the easiest ways to demonstrate it is with physical exercise, but pretty much any other plasticity that you can introduce will change your brain positively. Learning a new language, learning a new skill, learning a new sport, anything that engages your brain in a positive way that you're actually acquiring, that you're actually learning, is going to introduce this plasticity. So those are all wonderful things. So now this all sounds very positive, but we all know that the reality is more complex than that. We know that our brains do change as we get older, and sometimes in ways that we're somewhat uncomfortable with. So how do we reconcile that with all these positive things that I just told you? Well, I want you to think about what happens in the older brains, not as deterioration, not as degeneration, but rather as an adaptation of speed versus selectivity. Now, I will not deny at all, as we get older, our processing speed goes down. Our ability to do things quickly, to pick up on things quickly, to learn things quickly, yeah, that goes down. But there's something else that goes up, and that is our selectivity. Our brains become a lot more selective as we get older. Not everything is learned willy-nilly. Not everything is important. In some ways, we've learned to be more wise, able to use our resources in a wiser way, because the brain is a limited resource system, so it has to allocate those resources where it matters. So we become much more focused on what matters. So now that we know that, the question is, what matters? What is it that should matter to us as we get older? What kinds of things make the brain tune in and try to learn and remember well into older adulthood? There's a few of them. We select for challenge. When things are challenging, they tend to engage the brain, and the brain wants to learn. When things are not so challenging, the system is settled. It doesn't budge. It doesn't move when things are sort of weakly challenging. So you really want a serious challenge. When you think about it, if I'm learning something and it just feels so easy, you're not learning hard enough, right? And we all know this because at some point we've gone to the gym, we've worked with a trainer, and they say, hey, how does this weight feel? And you go, it feels easy. They go, okay, we need to up the weight. Otherwise, you're not working hard enough, right? The same thing is true for the brain. If it feels too easy, your brain's not going to be engaged. It needs a challenge. So things need to be harder by design. They also need to be relevant. They need to be important. You know, young adults learn all sorts of junk that is not really all that critical, right? They're encoding all sorts of things that are happening on the news, on social media, TikTok, Instagram, whatever. Yeah, one would argue all that stuff is not really important. But if it's relevant to us, if it's crucial for our survival, for our family, for the way that we think about the world, if it's relevant, our brain is really tuned in. And relevance is really by connection to our existing knowledge or existing goals. What do we want to accomplish? So for some, maybe knowledge about what's happening politically right now might be really important. For some others, it may not. That may not be part of their goals. So this is a highly individualized, highly personalized factor. Okay. The third one is also really, really important, and it goes back to the idea of practice. Practice makes perfect, is consistency. Repetition is important. It's not so much about the intensity, it's about repetition. Doing things repeatedly, being able to go through the exercise many, many times entrains that in the brain. Now, when you were younger, you might have needed fewer repetitions, but as we get older, we need more and more repetitions. So those are the things that we tend to select for. Okay, now that we have all of this at our disposal, we know we're empowered, and we believe, I hope, that our brains are capable of so much more than sometimes people give them credit for. The question is, what is the recipe for success? What can we do to be able to protect our brains as we get older? And there's a long laundry list of things that you can do, but I'm just going to give you my favorites, my top ones, and I base that on the ones that have the most scientific evidence in their favor. I'm not going to tell you about vitamins. I'm not going to tell you about minerals. I'm not going to tell you about, things that you should ask your doctor for. I'm going to tell you about the stuff that you can do literally a moment after we're done. Okay? First one, you all know this. Physical activity, exercise, individually, in groups. In groups is better. With someone is better because you're able to capitalize on social engagement as well. So exercise, I apologize if it's a little jerky on the screen. It looks good on mine, but it may be a little bit just in transmission here. But physical activity and exercise, we know from clinical data, epidemiological data, clinical trial data, that it reduces risk for Alzheimer's disease and protects the aging brain. Social engagement is another huge one. Being able to be engaged socially, leisure activities, whether it's playing chess or hanging out with friends or being part of a knitting club, book club, whatever it is, as long as you're around other people. Even if you don't end up talking to them as much, but just being in their presence. Turns out that as a species, we are so incredibly social that actually being isolated is so unnatural for our brains. Our brains don't like that at all. They like to be around people. Now, I realize that being around some people may actually cause stress, right? So I'm not telling you go hang out with people you really dislike, right? Be careful with who you spend time with. But as long as it's all comfortable and happy, spending time with people is going to be helpful. And again, we know this from clinical and epidemiological studies. Social and cognitive stimulation reduces risk for Alzheimer's disease. Okay, what about food? There are so many diets out there. Everybody's got a diet prescription. There's a billion different diet books. And all of that reduces to one thing and one type of diet that probably has the best evidence in its favor. You've probably guessed it already looking at the screen at all of these colorful things and the fish right in the middle, the Mediterranean diet. The Mediterranean diet is characterized by lots of leafy green vegetables and fruits. It's healthy oils. It's reasonably low on carb, but mostly whole grains, and very little red meat, mostly protein from fish sources, which tend to be far healthier. Now, there's variants on this. There's also the MIND diet, the DASH diet. They're all variants on this that are made specifically for groups of individuals who might have heart issues or diabetes or whatever it may be. So you kind of need to customize, tailor make a version of this. But the general principle, when you think about what is in the Mediterranean diet, it's all the stuff that we grew up recognizing is pretty healthy for you. So it's not rocket science. It's not anything out of the blue. It's not anything that's new to you. Hopefully, you've heard about this many, many times. And the reason why I like the Mediterranean diet so much is because, again, even though other diets have been tried, when you look at clinical trials that have randomized people to the Mediterranean diet versus others, This one tends to be the one that is associated with the best outcomes, meaning later age of onset for Alzheimer's disease, better outcomes even for patients with Alzheimer's, and reduced risk for pathology. Okay? And then finally, this one is really, really important. We all do it. Every species under the sun does it. And somehow we still don't understand why. We still don't fully understand why is it that we have to sleep. I'd be very interested if anyone has a good theory. But it turns out for some reason or another, sleep is so crucial, so important. Being able to get a good night of sleep is so important for brain health. I can't even begin to tell you. And now this has been demonstrated in so many different kinds of studies. And I'll give you kind of a couple of clues as to why this might be important. One, we know that when we sleep at night, our brains continue to operate on the things that we learned and remembered during the day. So being able to what's called consolidate memories, hold on to them and store them, that happens while we sleep. So that's thing one. Thing two, it turns out that one of the most important functions of sleep is what's called glymphatic clearance. It sounds a lot like lymphatic clearance, but glymphatic is the word, starts with a G, and the G stands for glial, and that's a type of brain cell. It is essentially clearing out of all the waste that builds up in our brains during the day. We do that at night. And one of the things that we clear at night is amyloid pathology, one of the key hallmark pathologies of Alzheimer's disease. We produce a lot of it during the day, we clear it during the night. And one of the challenges that we see in Alzheimer's is you produce a lot and you don't clear enough. So then it aggregates and builds in the brain. And one of the reasons one that might be the case is because of sleep disturbances, sleep disruption, either from insomnia or obstructive sleep apnea. Anyone who, for example, snores while they're asleep and their partner picks up on it, you're not getting quality sleep. Anyone who has to wake up a lot during the night for one reason or another, you're not getting quality sleep. And if you suspect that you have sleep problems, you feel sleepy during the day, or hopefully never fall asleep at the wheel or anything like that, you should get a sleep study done, an overnight assessment, so you can figure out if there's a sleep problem that needs to be addressed. Sometimes it's as simple as getting a better pillow or a better mattress or reducing the temperature slightly. Some things can be very easy fixes, but sleep problems are detrimental. So being able to maintain healthy sleep, both quantity and quality, is really important. Now, all of this in mind, the question is, can we use all of these things to our advantage and be able to live well into 100, 110, 120? Yeah. This is John Louis Calment, the oldest known person to have lived on this planet, lived to be the age of 122, never had Alzheimer's disease, had pathology in her brain. On autopsy, they discovered the pathology, but did not have any clinical symptoms of Alzheimer's disease. She would say, always keep your smile. That's how I explain my long life. And she had a very, very happy and long life, surrounded by the love of family and friends, never wanted for anything, did not have a lot of stress. And here's the part that I hate mentioning to people, but I feel I must mention it to you. She was also a smoker, not endorsing smoking at all, but it just shows you how much resilience, how much compensatory adaptive scaffolding, how much reserve her brain had to allow her to deal with all of that well into 122. She also loved chocolate, by the way. Okay, so now we know successful aging is real. This is all very positive. We have a recipe. The big question I always get asked is, why do we still have no cure for Alzheimer's? Well, you'd think with all of these things in place, we should have been able to stop this thing dead in its tracks. And there are so many answers to this question, and this will be a whole other talk. Heck, it's a whole day that you can come spend with me if you'd like. Tell you everything there is to know about why we don't have a cure for Alzheimer's disease. But I'm going to leave you with a couple of just parting notes about Alzheimer's disease and why we don't have a cure, because I think this is what really needs you and your voice and your advocacy to be able to make a difference. See, our field, I think, has been thinking about this the wrong way. We've always been thinking about Alzheimer's disease as one thing. And I talked about so many different ways to build adaptive resilience today. Well, the same is true for Alzheimer's. It's not one thing, it's so many things. It's not one disease. It is so many diseases that are disguised under the same umbrella. The approach that we're taking to it, and some of my colleagues in the field are starting to kind of pay attention to this, is that we can't just have one treatment. We can't just have one cure. We really have to think about this as a highly individualized condition. This is the promise of precision medicine, and this is what we're trying to do right now in my laboratory. We start by assessing all of the person's risk factors. We want to understand age, genetics, heart health, exercise, all of their exposures, their diet, their sleep, their access to resources, all of their health comorbidities, other health conditions that you might have as you're getting older. Do a comprehensive assessment of all of those factors. And then we do incredibly comprehensive biomarker evaluations. That's what we specialize in. We use brain imaging, blood tests, digital tests like memory tests that you take on an iPad, for example. All of those things are intended to give us an idea of what the active mechanisms are in the individual. In addition to amyloid plaques and tau tangles and the things that you've heard about for decades now, there are so many other subtle changes that happen in the brain. Inflammatory changes, the brain's immune system changes in Alzheimer's disease, the ways that neurons, brain cells communicate with one another, what's called excitability, that changes. Our vascular flow, our blood supply that goes into our brain changes as we get older. Our metabolism changes as we get older. And all of those things change in subtle ways and different ways across individuals. But once you have a clear idea of the balance of all of those factors and how they're changing, you can start to feed that information into new drug development, new clinical trials. And my hope, I've been preaching this to a lot of people in pharma and government and so on, and saying, this is the kind of work that we need to now allocate our resources to. We need to do smarter clinical trials, smarter drug development, smarter testing that actually respects the fact that we're not going to have just one silver bullet, one size fits all solution. We need the right solution for the right groups of individuals. For example, if I go down the path to Alzheimer's disease, my Alzheimer's disease, I can tell you right now, based on my health conditions, is much more likely to be of an immune nature, an inflammatory nature, because I have an inflammatory condition. So if I were to get it, it's much more likely that it's going to be of the inflammatory subtype. And a treatment for me might be much more likely to work if it's focusing on inflammation rather than other things. For others who might have heart disease or a history of stroke, it might be more vascular in nature. For others who have maybe metabolic syndrome or diabetes, it might be metabolic in nature, and so on. Now, this is sort of an uncomfortable truth for many of our colleagues in pharma who would love to have a blockbuster medicine, one size fits all, because that's where the big bucks are. But the reality of the disease is different. Okay, so this is the work that we're doing at UC Irvine. If you are interested in our work and would like to participate in studies, hear more, you can go on our website, beacon.bio.uci.edu. Beacon is our collaboratory. This is a large-scale NIH-funded study, taxpayer-funded study. It is intended to monitor individuals who actually don't have Alzheimer's disease. They're coming into this as cognitively healthy individuals, but we're monitoring them over time and measuring all of the things I talked about on the last slide and trying to understand what are the things that are going to predict their path and how can we develop better markers and better therapeutics for individuals. It's been a very productive research study. I am the principal investigator of it, so I direct that program, but I have a large team that works with me. This is just some of us here that are based at Irvine, but we actually have a large international team that works on this as well. And just some of our recent findings looking at, how your sense of smell changes as you get older, how sleep is linked with Alzheimer's risk. And this one was actually a really nice study that we did several years ago, showing that even a walk as brief as 10 minutes, and I'm talking walk, not jog, can be sufficient to protect you from Alzheimer's disease. Okay, with that, I did not mean to actually have this slide here. I'm actually going to stop it here. I had a blank slide next. So I'm going to stop sharing and say thank you, and I'm happy to take questions. I think we have about 10